Oceans are some of the most efficient CO2 absorbers out there, sucking out 25% of our emissions each year.
Ocean-based carbon capture is the idea that we can remove carbon dioxide from the atmosphere by accelerating natural processes.
Keeping even vaguely in line with our global warming targets means cutting our emissions. But even that won't be enough. So we'll need to go further. And for that, carbon capture would have to scale up fast.
Within the community that's starting to develop carbon removal technologies, it's becoming a bit of a consensus that we'll likely need gigatons or billions of tons of carbon removal annually by 2050. This is an absolutely enormous challenge. There's about 8 gigatons of coal produced annually. This is one of the most handled materials in the world. So if we're going to scale the carbon removal industry, it needs to become something along the lines of the coal or the oil and gas industry.
Ulf Riebesil is among the growing number of scientists who believe that ocean-based carbon removal could have a large role to play here.
Certainly the ocean carries a very high potential for CO2 removal, but we have very little understanding at the moment of what the potential risks and side effects of that are.
We're now here just south of Bergen in Norway, where we had a 55-day experiment, which we just completed now.
Ulf and his team are running a study funded by the European Union, testing out a method called alkalinity enhancement, which essentially is changing the water's pH in the hope of boosting its CO2 absorbing powers. pH is a scale which shows how acidic something is. It goes from acidic at the lower end to alkaline at the higher end, in case you forgot your high school chemistry. Oceans have become more acidic as they absorb more carbon dioxide. The team submerged 10 mesocosms. Those are giant, 20-meter-long test tubes filled with water from the ocean. Then they added different concentrations of chemicals found in natural rocks like lime or volcanic olivine to change the water's pH and make it more alkaline.
So we simulated alkalizing seawater in our mesocosms, trying to see whether there's any harm done to marine life, and to test whether it takes up more CO2.
Think of opening a bottle of sparkling water. That hiss you hear is the gas escaping because there's more of it in the bottle than in the air. The reverse happens with oceans absorbing atmospheric carbon dioxide.
Because we've been emitting CO2, there's now this reverse imbalance where there's too much CO2 in the air compared with the water, and the water is starting to absorb CO2 from the air.
All of this CO2 being absorbed is making the water more acidic. This not only wreaks havoc on marine life, but it's also slowing down the ocean's intake of carbon dioxide. Alkalinity enhancement could counteract all of this. By dumping a huge amount of pulverized minerals into the ocean every year and turning the water more alkaline, it would increase the rate of natural chemical reaction, which breaks down CO2 into compounds, making more room for the ocean to absorb additional CO2.
Alkalinity enhancement kind of seems like a chemical solution, but it's a natural process. Rocks are weathered through reaction with water and CO2. And that releases alkalinity into fresh waters, and via rivers, this extra alkalinity is supplied into the ocean. The process is very slow though, and the idea of alkalinity enhancement is to speed up this natural process.
It's the last day of the study, and the team is retrieving the mesocosms and sending the samples for analysis in partner institutions around the world. It's a method that still requires an incredible amount of fine-tuning.
There's a whole set of unknowns. The mineral needs to be ground very finely, otherwise it will just sink out to the ocean floor and not be of any use for CO2 sequestration. If you increase alkalinity too high, that counteracts the effect you want to achieve. It releases CO2 instead of sequestering CO2. And then, of course, there's the risk of harming marine ecosystems.
Hacking the oceans like this is seen by many as borderline, if not straightforward, geoengineering, and there is criticism in the scientific community that it could unleash yet another environmental catastrophe. To minimize any potential impact on the environment, some companies are trying to do ocean-based carbon capture without an ocean. One of them is betting on algae, an organism which removes carbon from the atmosphere for a living.
Algae are the original carbon sequesterers. 80 million years ago, algae that grew on very large scale in inland oceans formed the oil deposits that we are mining today. They are, in nature, sinking out from the ocean, collecting in the seabed, and then stored there for millions of years. And we are just trying to repeat that process deliberately and maybe a little bit more quickly. Algae are plants. They photosynthesize, which means they take carbon dioxide and sunlight and turn it into sugars and starches and cellulose and bodily functions. And so in the process, they release oxygen, and that carbon is then embedded in the biomass in the cells.
Thanks to photosynthesis, algae are another way the ocean absorbs CO2, and there are hundreds of thousands of different kinds of them. People have tried growing algae for biofuel for years, and often these projects were using species that were best suited or even engineered for oil production. Now, they were brought straight from the lab to the desert, but organisms would struggle in these new intense conditions. Ponds would get contaminated with local species, and the projects would fail. And failure is so common that the oil giant ExxonMobil, which has funded algae research for years, believes this technology is still decades away from being able to scale. But Brilliant Planet claims to have a solution. Strip down as much technology and engineering as possible and let nature take over.
Our system is very natural, which means we do not pump in lots of nutrients, we do not pump in a lot of CO2, and we spent a lot of time stripping out energy and complexity out of the system. We work with local natural algae. They are very good in that local environment. It's an open system, so we fully expect other organisms to be introduced into our ponds through the seawater. But it does not matter because our organisms are growing faster than they are. They're acclimated to those conditions, and they then overwhelm anything that comes into the ponds.
The company identified coastal deserts as optimal locations for their needs. Their pilot plant is based in Morocco, roughly a 6.5-hour drive from the nearest city. Majda Barosh is the laboratory coordinator there.
We start from just like one droplet of seawater, and then we continue adding natural seawater and nutrients until we reach bigger volumes. In the laboratory, the volume that we would like to reach would be around 100 liters or 60 liters, depending on the species that we're trying to cultivate. And then we transfer it to the greenhouse, where we keep diluting and adding natural seawater to it until we get to a volume of 40 tons of water. And then we transfer that to the outside pond till we reach the biggest pond that we have.
The whole life cycle is about 30 days, and the system is harvested every day. We remove all the algae and return the seawater back to the ocean.
We get what we call the biomass of the microalgae. We dry that, and we're working on burying the microalgae in the desert. The microalgae will be sequestrating the carbon from the atmosphere. Burying it would prevent it from going up in the atmosphere again.
In the future, Brilliant Planet is also planning to build much larger ponds on neighboring land in Morocco, and then onto countries like Chile, Peru, or South Africa. Seeing the small scale and the complexity working with governments in remote areas, it's hard to imagine this all expanding quickly. But Brilliant Planet wants to make their technology so easy and intuitive that they could just license it to local operators to run by themselves. The benefits of carbon removal will only materialize if we can scale up these technologies, and someone's going to have to pay for it.
This industry is only going to make sense if it can scale by selling offsets into a carbon market. If you're growing biomass in a pool, and then you take out the biomass, you dry it, and then you bury it, it's very easy to understand how much carbon is in the biomass. If, on the other hand, you're adding alkalinity and you're hoping that increases the rate of CO2 absorption from the ocean, that's a lot harder to tell. So that's actually what all the companies developing ocean alkalinity methods really need to prove, because at the moment, people are willing to bet on them and say, we'll pay you to develop the technology. But the reality is no one's going to pay for this if there's not a scientifically agreed upon way to measure the carbon that's absorbed through these methods.
In the end, we'll probably use a mixed bag of carbon removal solutions, where oceans might or might not play a part. But experts caution that before larger versions of these novel technologies can be considered, we should first know all the risks and whether they even work at all. And that will take time.
Whatever approaches will be used, we need enough information to take an informed decision. And of course, the decision needs to be taken not by us as scientists, but by society at large. And I see it as our responsibility to speed up obtaining that information.